Hello, today I'm presenting soldier vulnerabilities to toxic industrial chemicals, materials while in MOPP gear. My name is Philip Gidley. My co-author is Victor Medina. This is part of the Understanding the Environment as a Threat project, UET. The project manager is Dr. Krista Woodley. Slide 2, what is mission-oriented protective posture gear? It's MOPP gear. MOPP gear is a gas mask, has liquid repellent fabrics, and butyl rubber boots and gloves. Slide 3, at ERDIC, we're putting together a toxic industrial chemicals materials intelligence tool. It's a small database of about 350 chemicals. It provides chemical properties and toxicity data and also allows for chemicals to be searched based on industry information. Slide 4, military exposure guidelines, or MEGs, provide a groundwork for this effort. They're basically concentrations of chemicals that can be tolerated by soldiers. Slide 5, what are the vulnerabilities? We looked at the limitations of the gas mask and also quantifying the risks to soldiers while fording, both from inhalation from the water surface and dermal contact while the soldier is immersed in water. Slide 6, the M40 gas mask was first looked at, which has a C2A1 canister. We gathered properties for the C2A1 canister for our calculations. We're working under the assumption that the later gas mask designs, M50 and M51, have better or equal performance to the M40. This canister has an aerosol filter or HEPA filter to filter out particulates and an activated carbon portion. The activated carbon here on slide 7 is an ASZM-TETA or ASZM-T activated carbon, which has metals impregnated on the carbon surface. The activated carbon removes chemicals by physical absorption to the high surface area and by chemical reaction on the activated carbon surface. On slide 8, we first thought we could calculate which chemicals have a breakthrough time less than 8 hours and flag those as problem chemicals. To do this, we first started using the well-known Wheeler-Jonas and Mecklenburg equations and did our calculations in Excel spreadsheets. We used challenge concentrations set at 10% of the saturation concentration, and we set our breakthrough concentrations to the MEG values. And it turned out that almost all of the chemicals in our database, all 350 chemicals, were breaking through the gas masks in less than 8 hours, according to these spreadsheets. So we took an approach here on slide 9. These limitations to our spreadsheets were that the calculations weren't accounting for the chemical reactions on the activated carbon surface. And we also had many unknown chemical properties which were needed for these calculations. So in order to break up our 350 chemicals in Tickment into manageable numbers of equal numbers of approximately 120, where we could figure out which ones would be in the red category, the problem chemicals, we broke them up this way, where green category would be breakthrough time greater than 60. Yellow category would be breakthrough time in the range of 10 to 60 minutes, and a breakthrough time less than 10 minutes would be put into the red-orange category as being most problematic. Here on slide 11, the first critical chemical property needed is the vapor pressure or saturation pressure. If the saturation pressure is less than 10 millimeters of mercury, absorption capacity will be high, and there'll be strong physical absorption to the activated carbon, and we can put the chemical into the green category. Many solids, for example, which will be particulates that are filtered out by the HEPA filter, will also have a vapor pressure less than 10 millimeters of mercury. If the vapor pressure is greater than 10 millimeters of mercury, we need to get more information for the chemical or material. Here on slide 12, the next most important piece of information we need is the NIOSH chemical family. I've listed these at the top here: organic vapors, acid gases, base gases, self-polymerizing chemicals, hydrides, nitrogen oxides, and particulates. If the chemical is an organic vapor or a base gas, then we can calculate the breakthrough time using the multi-vapor program or multi-vapor app. We can also check the multi-vapor results with the Wheeler, Jonas, and Mecklenburg equations we used initially in the spreadsheets. If the chemical is one of the other NIOSH chemical families, an acid gas, hydride, nitrogen oxides, or self-polymerizing chemicals, then we need to use measured breakthrough times to put the chemical into a category. So the top table here are chemicals where we have measured breakthrough times. If the chemical of interest is one of those chemicals in the top table, then we can use the measured breakthrough time to put it into the proper category with considerations for the challenge and breakthrough concentrations used in those measurements. However, if the chemical is not in that top table, then we need to use the chemical that has the fastest breakthrough time within a family and make an inference to the chemical of interest. So, for example, if we have a nitrogen oxide that is not nitrogen dioxide, then we need to infer that the breakthrough time will be somewhere in the range of 27 minutes, putting it in the yellow category. And then we have to look at the challenge concentration and the breakthrough concentration used to get the measured breakthrough time and compare that to the likely challenge concentration and MEG value of the chemical of interest and perhaps make changes to the category accordingly. On slide 14, we used methods of calculating emissions off water surfaces from wastewater treatment plants to understand the flux off a water surface and the risk to soldiers while fording. On slide 15, if the chemical is an organic vapor, there's some pretty well established ways to translate the flux of the water surface to a concentration in air using volatilization factors. However, if the chemical is not an organic vapor, then we came up with this box model, a very simple method of translating the flux to the concentration in the air that the soldier will breathe. On slide 16, to calculate the dermal dose to a soldier while fording, we looked at 3 screening approaches, and I've provided the references here for those interested in these different ways of calculating dermal dose. And also there'll be a need to consider possible reactions on the skin surface, such as burns and allergic reactions. On slide 17, we did a Baltimore demo where we looked at an industrial site in Baltimore, and started asking what if some kind of accident happened there. This is an area of Baltimore that's highly industrialized. It has many other industries located here on Wagner's Point in the satellite image. Also, there's a lot of residential areas nearby. So we looked at the toxic release inventory for this facility owned by W.R. Grace, and we came up with what chemicals would likely be at the site. And then we went through the process of placing each chemical into a category to tell us about gas mass breakthrough. The first chemical, ammonia, has a high vapor pressure. It's a base gas. We could use multi-vapor to calculate breakthrough time, but we have measured breakthrough values for ammonia of 9.6 minutes, being less than 10 minutes, putting it in the red-orange category. Nitric acid was at the site, has a vapor pressure greater than 10. It's an acid gas. We don't have measured values for nitric acid, but we can compare to another acid gas, hydrogen cyanide, which has the fastest breakthrough time at 8 minutes, putting nitric acid in the red category. Comparing the challenge concentration, nitric acid has a lower MEG than the breakthrough concentration used for hydrogen cyanide, and the challenge concentration of nitric acid could be much higher than that used to obtain the measured values for hydrogen cyanide. So we keep nitric acid in the red-orange category. Titanium tetrachloride was at the facility in Baltimore. This chemical has a vapor pressure less than 10. That immediately tells us that this chemical should not be a problem for the gas masks. Hydrochloric acid or muriatic acid was at this facility in Baltimore. Hydrochloric acid has a very high vapor pressure. We have measured breakthrough times for hydrochloric acid of 448 minutes, which would put it in the green category. However, with such a high vapor pressure, hydrochloric acid could be at a much higher concentration than what was used to get the measured breakthrough times. So we bump hydrochloric acid from the green to the yellow category. Toluene was at the facility. Toluene has a vapor pressure greater than 10. It's an organic vapor. We use the multi-vapor app to calculate the breakthrough time of 61 minutes, which places it into the green category as not being a problem. Sulfuric acid was at the facility. Sulfuric acid has a very low vapor pressure, which means it should not be a problem and we can put it in the green category. However, fuming sulfuric acid can have a vapor pressure greater than 10. We don't have measured breakthrough times for fuming sulfuric acid, but we do have the ability to compare it to another acid gas, hydrogen cyanide, where the breakthrough time is 8 minutes, putting it in the red-orange category. The MEG value for sulfuric acid is also lower than the breakthrough concentration used for hydrogen cyanide in the laboratory. Also, the challenge concentration is probably similar to what was used to obtain the measured values for hydrogen cyanide. So we keep sulfuric acid in the red-orange category. Ammonium nitrate, we were unable to obtain a vapor pressure for ammonium nitrate, but we know that this chemical is a white crystalline solid at solid standard temperature and pressure, which means it's a particulate that will probably be filtered out by the HEPA filter before reaching the activated carbon. We did notice that there's a vapor pressure of over 10 for ammonium nitrate dissolved in water. So we might want to consider ammonium nitrate in the fording situation, and we also noted that ammonium nitrate had a very low MEG value, so we bumped it up from the green to the yellow category. Chlorine has a high vapor pressure. It's an acid gas, but we have measured values for chlorine with breakthrough times of 280 minutes, which would put chlorine in the green category as not being a problem. However, chlorine with a high vapor pressure could be at a much higher challenge concentration than what was used to obtain the measured experimental values, so we bumped chlorine up from a green category to the yellow category. So looking at all these chemicals, it looks like getting more measured breakthrough times for some of these common acid gases like sulfuric acid and nitric acid would really be helpful. Because I think if we actually had measured values for those common acids, we could bump those out of the red-orange category and maybe put them in the yellow or even green category. Moving on to slide 19, just wanted to emphasize how the threat is real. So this area of Baltimore that's highly industrialized, Wagner's Point, has had a history of incidents. In 1998, there was an explosion sending plumes of aluminum chloride and hydrochloric acid into the air. In 1979, a railroad car overturned, spilling 1,000 gallons of sulfuric acid. And in 1965, a site owned and operated by Continental Oil Company at the time had a large fire. So this is not just a threat for soldiers who are operating in urban environments overseas, but it's also a real threat to civilians and to civilian first responders. Thank you for your time today. If anyone has any questions, I'd like to take questions at this time. I've also provided my email and my co-author Victor Medina's email, so you can send us any other questions that you think of later. Thank you very much.